Oh, you are really study hard. Let's begin with the core of data visualization in Python, Matplotlib. In our increasingly data-rich world, the ability to transform raw numbers into meaningful insights is not just an advantage, it is a necessity. Matplotlib stands as a cornerstone library, offering unparalleled flexibility and power to create everything from simple line graphs to complex multi-panel figures. It's designed to work beautifully within the Python ecosystem, making it an indispensable tool for anyone serious about data analysis and communication. Why do we even bother with visualization? Because our brains are simply better at processing pictures than paragraphs of text or columns of numbers. Think about it. When you see a chart showing a company's revenue growth, you grasp the trend instantly. Trying to understand that same information in a spreadsheet takes significantly longer. Visualization leverages this cognitive strength, allowing us to spot hidden patterns, identify outliers, and communicate complex findings with clarity and speed. It's the bridge between raw data and actionable insights, enabling decisions grounded in evidence rather than intuition alone. Whether it's a scientist analyzing experimental results or a business analyst presenting quarterly performance, effective visualization is key. Now, let's peek under the hood at the Matplotlib ecosystem. At its heart is Matplotlib, PyPlot, the workhorse module you'll interact with most often, providing a simple interface for creating plots. But beneath that lies the more powerful object-oriented API centered around the figure and axis objects, offering granular control perfect for complex visualizations. This core functionality is rendered by various back-end systems which handle the actual drawing on different platforms. And then there are the specialized toolkits, like mplot3d for adding depth to your plots, or basemap for geographical data, extending Matplotlib's capabilities. Crucially, it plays well with others, integrating smoothly with the rest of the Python data stack, making it a central piece of the analytical puzzle. All right, let's get practical. Getting started with Matplotlib is straightforward. First, make sure you have Python installed. Then use pip Python's package manager to install Matplotlib. Just one command, pip install Matplotlib. To verify it's working, you can run a quick script importing Matplotlib and printing its version. For those managing multiple projects, I highly recommend using virtual environments like Venv or Conda. This keeps dependencies isolated and prevents conflicts, ensuring a clean setup for each project. It's a small step now that saves headaches later. So, what kind of visual stories can Matplotlib help us tell? We've got a whole arsenal. Line plots are your go-to for showing trends over time or ordered categories. Scatter plots are fantastic for exploring relationships between two variables, revealing correlations or clusters. Bar charts are perfect for comparing quantities across distinct groups. Histograms give you a snapshot of a single variable's distribution. How frequent are different values? P-charts show proportions, though use them judiciously. Box plots summarize distributions and highlight outliers efficiently. And heat maps use color intensity to visualize complex data matrices, great for correlation or density. Each plot type serves a specific purpose in understanding and communicating data. Let's start with line plots, fundamental for tracking changes. The basic syntax is plot xy, where x and y are your data arrays. You can customize the appearance using format strings for color, markers, and line styles. Imagine plotting temperature fluctuations over a day. Here's a simple example using NumPy to generate sine wave data simulating temperature changes. We call PLT, add axis labels and a title, and finally PLT, to display the plot. It's straightforward yet incredibly powerful for visualizing trends. Moving on to scatter plots, ideal for exploring relationships. The function is pli, scatter xy. Similar to line plots, you provide x and y data. But here you gain more control over individual points, specify their size, s, color, and even use a color map for color mapping. Let's say you want to analyze if study hours correlate with exam scores. This example generates random data with a positive trend. The scatter plot visually suggests this relationship, potentially hinting at a correlation. It's a powerful first step in exploratory data analysis. Bar charts are essential for comparison. Use PLT, bar x height. Here, x defines the positions of the bars, typically corresponding to categories, and height specifies their lengths, representing the quantity you want to compare. You can also adjust width, alignment, and even stack bars. Consider comparing sales figures for different products. This example uses categories A through D and corresponding values. The bar chart immediately shows which category performed best, making comparisons intuitive and clear. Simple, effective, and widely used. Histograms are your tool for understanding data distribution. The command is plt, histon. You pass in your data array X. Key parameters include bins, which determines how many intervals or bins to divide your data into, range to set the minimum and maximum values for the bins, and density to normalize the histogram so it forms a probability density function. Let's look at exam scores. This example generates normally distributed scores and creates a histogram with 10 bins. The shape of the histogram tells us about the spread and central tendency of the scores. Is it skewed? Bimodal? Histograms provide crucial insights into the underlying structure of your data. Okay, we've covered the basics. Now, let's talk about taking control and making our plots truly professional. Beyond the simple functions, Matplotlib offers deep customization through the figure and axis objects. This allows us to meticulously tweak every aspect: titles, axis labels, tick marks, legends, grid lines, colors, fonts, and more. We can add annotations and highlights to draw attention to key findings. And finally, we need to know how to save these beautiful creations in various formats. This level of control is what separates basic plots from compelling publication-ready visualizations. To achieve fine-grained control, we move beyond the stateful pyplot interface and directly manipulate figure and axis objects. Start by creating a figure with plt, fig size equals, specifying the overall size. Then, add one or more subplots, axes, using fig. Add subplots. For a simple plot, fig. Add subplot 111 creates a single axis object. For multiple plots, you specify rows, columns, and index. Once you have the axis object ax, you use methods like ax instead of plt. This approach is essential for creating complex layouts, like the two-panel sine and cosine wave example shown here. It gives you precise control over the arrangement and content of each plot panel. With our axis object ax, we can customize almost everything. Set titles and labels using ax. Set title, ax. Set x label, ax. Set x label. Fine-tune the ticks and their labels with ax. Set, x ticks, ax, set, y ticks, and the corresponding label functions. Control grid lines with ax.grid. Add legends using ax. Add legend, often after plotting multiple lines with labels. Look at this example. We customized the trigonometric plot with specific x ticks labeled with pi values, added grid lines, and included a legend. These details make the plot more informative and visually appealing, guiding the viewer's eye and enhancing comprehension. Making your plots visually appealing isn't just about function, it's about aesthetics too. Matplotlib offers styling options. You can apply predefined themes using PLT style. Use like ggplot or Seaborn, which often give plots a more polished look right away. Beyond themes, you can manually customize colors using names, hex codes, or RGB values. Change fonts for titles, labels, and ticks. Adjust marker shapes, sizes, and line styles for different data series. The example here applies the Seaborn style and then further customizes the colors and line widths for the sine and cosine plots. Styling makes your visualization stand out and align with your presentation or publication standards. Sometimes, you need to point out something specific in your plot. That's where annotations come in. Use ax, text, x to add plain text at coordinates x, y. For more complex highlighting, ax annotates xy, ext arrow props lets you place text at xy text and draw an arrow pointing to xy. You can also highlight regions using AX-AX-HS span for horizontal spans or AX-AX vertical spans. The sine wave example demonstrates adding text directly at the peak and using an annotation with an arrow to explain the maximum value. These tools help guide the viewer's attention to critical insights embedded within the data. Finally, you've created a brilliant plot, but it needs to be shared or saved. Use PLT, Save Figfilename, to export your figure. Specify the file name and the desired format, like PNG, JPEG, PDF, or SVG. Control the resolution using the DPI parameter, crucial for print quality images. You can also enable transparency with transparent equals true if needed. The example saves the sine wave plot as a PNG file named sinewave, with a high resolution of 300 dots per inches. Always remember to save your work before closing the script or the plotting window, especially when working interactively. And that brings us to the end of our whirlwind tour. As you've seen, Matplotlib is a remarkably versatile and powerful library for bringing data to life. From fundamental plot types to intricate customizations and professional styling, it provides the tools to effectively visualize almost any dataset. Mastering Matplotlib isn't just a technical skill, it's a critical competency for anyone working with data today. Keep exploring, experiment with the examples, and don't hesitate to dive into advanced topics like 3D plotting or animations. The journey of data visualization mastery continues.